Thank you for introduction, Chairperson. First, I'm going to introduce adversarial attacks on AI as a background. Second, we propose a defense methodology against the adversarial attacks. However, we are concerned about the potential further attack scenarios. The verification results are going to be present at third. Then we propose an improved defense methodology. Fine, I will conclude my presentation. As a background, IoT is connecting the human and object. It's sharing a lot of knowledge and information. Huge amount of information from sensors are going to be accumulated in cyberspace. This information will be analyzed by AI without the human intervention. Analysis result will be fed back to the human in the physical space. In particular, the demand for the real-time response, edge AI, is increasing. And the benefit of attacking edge AI are also increasing. So reliability and security for edge AI is required against these malicious attackers. We are studying adversarial attacks. As you know, in the normal image recognition with clean image, a rabbit is classified as a rabbit. However, the adversarial attacks inject a small perturbation into the sensor signals in order to misclassify AI recognition. Adversarial attacks use a small noise called adversarial perturbation. However, in the attack scenario, with adversarial perturbation, a rabbit can be misclassified as a police van. This perturbation is small. This attacked image looks like rabbit for humans. Next, I'm proposing a defense methodology. In the proposed defense methodology, deterrence noise and denoising autoencoder called DAE are added prior to CNN. DAE is a neural network trained to remove noise. The added disturbance noise is removed by DAE. Thus, the rabbit recognized as a rabbit. In the case of adversarial image, the small adversarial perturbation is easily disturbed by adding noise. Therefore, the adversarial perturbation is also reduced by the DAE. Thus, the attacked rabbit can be recognized as a rabbit. We have verified the recognition accuracy under the adversarial attack. The attack used the tiny ImageNet as a dataset, and the unit structure was DAE, and the ResNet 50 was CNN. Tiny ImageNet is an image classification task. The attacker predicts the disturbance noise and makes a small change to the image. This is the simulation result. The y-axis represents classification accuracy, and the x-axis represents the amount of adversarial perturbation. The accuracy at x equal to 0, the case when the attacker does not attack. We show the red line. In typical case under the adversarial attacks, the accuracy decreases steeply. This indicates that the attacker can cause a misclassification with a small perturbation. So the blue lines as the perturbation increased from 0.525 over to 155. The accuracy decreases gently compared to the red line. This indicates that attacker must add a significant amount of perturbation to cause high probability misclassification. In other words, disturbance noise helps to remove the adversarial perturbation by the DAE. However, we are concerned about the further attack scenario. As long as the disturbance noise is generated by the computer algorithm. The attacker may be able to predict the noise from the initial value and the internal state. Moreover, the algorithm of the DAE and CNN are typically publicly available. As a result, the attacker can revise the adversarial perturbation in order not to be removed by the DAE. Consequently, the attacker rabbit once again misclassified as policeman. This is the simulation result. As shown in the previous slide, disturbance noise helps to remove the adversarial perturbation by the DAE. However, when the disturbance noise is predicted, the accuracy decreases steeply. This indicates that the attacker can cause a misclassification with a small perturbation. This curve is very close to the case without our proposed defense. In other words, predictable disturbance noise does not work well. Next, I'm proposing an improved defense methodology. We propose to use a pixel reset noise generated in the image sensor as a disturbance noise. When capturing an image, both the illuminate signal and the reset noise are read out. By combining the signal and noise, the image sensor output is noisy image instead of the clean image. Then the DAE can remove this noise. Furthermore, the attacker cannot predict the disturbance noise because reset noise based on thermal noise. Thus, the perturbation and disturbance noise is reduced by the DAE. Therefore, attacked rabbit can be recognized as a rabbit. Here, I'd like to explain how to read both illuminate signal and reset noise. Typically, CMOS image pixel consists of the photodiode and transfer gate, reset transistor, source follower, and select transistor. First, the illuminate signal are read out in the same way as the conventional CMOS image sensors. The floating diffusion node is reset toggling the reset pulse. Then, the photoelectrons are transferred from the photodiode by toggling the transfer gate pulse. The difference between the reset level and signal level is read out to remove the pixel reset noise. Second, the reset noise is read out. The floating diffusion node is reset by toggling the reset pulse twice. Once and twice. The difference between two reset levels result is utilized as a disturbance noise. We have measured the 62 million bits of the reset noise to verify its randomness. We have verified the randomness of the CMOS image sensor reset noise using the NIST 822 standard. NIST 822 is statistically evaluates the quality of random number generators. This framework includes the 50 different tasks. We verified the measures of 62 million bits of the reset noise. The reset noise passed almost all tests with a high probability, and we confirmed the randomness of the reset noise. Thus, we can conclude that the reset noise can be effectively utilized as a disturbance noise and in adversarial attacks. We have verified the recognition accuracy under the adversarial attacks. However, this time, non-predictable reset noise was added to the image. When epsilon equals 2/255, the recognition accuracy improved by 30.5%. This means that defense success rate is increasing. On the other hand, the side effect of adding noise is degradation accuracy for clean image. However, the degradation was only 3.8%, even though the noise added to the clean image. These three figures show the example image. To humans, all objects look like buffers. However, the CNN misclassified freight cloud due to the adversarial perturbation. In contrast, the AI can recognize the buffers because the non-predictable reset noise was added to the disturbance noise. Let me summarize my presentation. We have proposed a defense method against adversarial example attacks. For that, we use a DAE and disturbance noise. And the disturbance noise is based on the thermal noise, its image sensor, and it is non-predictable. According to the simulation result, adversarial example attacks success when the disturbance noise is predicted. However, when the non-predictable thermal noise is utilized, the accuracy was recovered by around 30%. That's all. Thank you for my kind attention.